Welcome to Data Science 1, Probability, Discrete, Cumulative Distribution Functions. All right, so we're going to get rolling here. Things we need to remember. We need to remember what a random variable is, which is really simple. It's just how do we measure our outcome? Experiment happens, how do we measure it? Probability distribution. What are the probabilities associated with those measurements, essentially? And the properties of probability distribution functions, they're always positive and they sum to 1. So it's pretty easy. Okay, so properties of random variables that are discrete. A single value is easy to calculate, right? We just plug in the number directly into the probability distribution and we get at the number. Super easy. If we have a range of values, then we have to add them up. That's how probability works. That's one of the axioms that says if you can break it up in a way that you can not have anything overlap, then just add it up. So that's what we did here. However, this can be problematic if we have to do lots of individual calculations. So that leads us to this idea of what's called a cumulative probability distribution function. And it looks a little more complicated, but it really isn't at all, okay? So basically the idea here is now we're going to use capital F versus little f, and this will make a big difference as we go along here. So keep in mind, when you see a capital F, we're talking about cumulative, and when we're talking about little f, we're talking about just the individual probabilities. And here we're going to define it to be the probability that x is less than or equal to some little x, okay? So instead of individual probabilities, we're interested in the probabilities to basically the left, anything lower than it or equal to it. And we just add up those probabilities just like we would have before. Okay, sometimes this can be analytically calculated, and other times we'll need a computer. But either way, these make calculating probabilities really, really easy, and you'll be using these regularly if you ever have to look at a table, because that's typically what they are. All right, so here's an analytic example. So suppose X is the number of failures until the first success. Okay, this is geometric. And if we go through the work, this is where you'll end up. So if you go through all this, all your math, I'm not going to go through the math, but I'm going to say this is where you end up. And that's what makes this easy. So suppose that we're interested in, since this is our CDF, this is just plug in some numbers and bingo, you'll get the answer out. So here's an example. Maria is interested in the number of days before a seed germinates. She thinks the probability is about 0.07 of success on any given day. Okay, what is the probability that the seed will germinate before 12 days? Well, I could add up all of them, right? There would be 0, 1, 2, 3, 4, all the way up to 12 and do 12 computations, or 13 computations actually. Or I could just plug in the number. Okay, so it says before 12 days. So now you have to pay attention to the inequality. Before 12 days is actually 11 days or less. Okay, plug that in, plug that in, plug that in, and we end up with 0.5814. Notice we didn't have to go through and calculate all of them. Okay, we were able just to plug it in here instead of doing all the probabilities individually. Okay, suppose we're interested in changing this and saying it's between 1 week and 3 weeks. That's essentially what this is saying, inclusive. So this is a geometric experiment again, and this is the probability we're interested in. Okay, well, we can break this up. If we have it this way, it's the probability that we're less than or equal to 21 minus, let's just remove anything that's less than 7. So chop away anything less than 7, which happens to be 6 or less, right, because 7 is inclusive here. Then we just plug it into F of the cumulative distribution, capital F of 21 minus capital F of 6. Plug in all the numbers and you end up with this probability, 0.4291. And notice how much easier this is than trying to calculate 14 or 15 numbers in between these two. It makes your life so much easier if you're calculating across a range of values, and later it will be imperative that we do this. We must work with a cumulative distribution function in lots of cases because it just makes life so much easier, and that's why we use them. All right, so here, this is the probability that the seed germinates between 7 and 21 days. Now, right now, this might seem a little bit confusing. It'll keep showing up off and on, but right now, we're just trying to demonstrate what it's for and give you some vocabulary. All right, so If it's analytically tractable, then computation can be very fast. When I mean analytically tractable, I mean we can come up with a formula for it. There are times when you can't come up with a single value for it, so what we would do is use a numerical approach. And we'll talk about those later. But right now I'm just trying to give you the idea. And this allows us to calculate calculate probabilities for complex events, right, between things, or things where it's going to take a lot of individual computations. The cumulative distribution function can bail you out big time. All right, so we're going to move on and see what's in the next video.